In a previous lecture, we talked about cyclic subgroups of a group. So recall that if G is a group and A is an element of G, then the cyclic group generated by A is denoted this way with the angle brackets, and it's the set of all powers of A that we get when we take all integer powers. So this is a squared, a cubed, etc., as well as a to the 0th, which is the identity, a inverse, a to the negative 2, etc., etc., all possible powers of A. This is when G is written multiplicatively. And when G is written additively, we could write it the following way. It's the set of all multiples of A. The things that you get by adding A or subtracting A over and over and over again. And this is when G is additive. Cyclic groups are groups that are themselves one of their own cyclic subgroups. So we looked at that definition last time. So if G is actually equal to the subgroup generated by A for some A in G, then G is called a cyclic group, and A is called a generator of G. Generally speaking, a group will have more than one generator. Usually, a group will have several generators, possibly very many generators. So let's look at a couple of examples, and we'll see eventually that the two examples we're about to give are in a very precise sense, the only cyclic groups, in that every cyclic group will behave like one of these two that we're about to write down up to a relabeling of the elements. So examples of cyclic groups are the integers with addition and the integers mod n with addition are cyclic groups. We have that Z with addition is generated by 1. And how do we know that? We know that since every element of Z can be written as n times 1 for some n. And remember that the n's that we use to multiply here can be positive or negative. So another way of thinking about what we're saying here is that Z contains, well, it contains its identity, of course, and it contains 1, the generator. And then we say, well, what do we get if we keep adding the generator to itself over and over again? Well, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, so forth and so on. But we also have to take the negative multiples of 1. So in other words, we have to subtract 1 over and over again. So we can get negative 1, negative 2, negative 3, negative 4, and keep going there. So that means that 1 is a generator for Z. Now, it's not the only generator for Z. There's one other one, but many numbers are not generators for Z. So for instance, 2 is not a generator for Z. So Z is not equal to the cyclic subgroup generated by 2. And that's since, for instance, 3 is not in the cyclic subgroup generated by 2. The cyclic subgroup generated by 2 is going to be the set of all multiples of 2, or in other words, all the even numbers, which is not all integers. And in particular, the cyclic subgroup generated by n is going to be the set of all multiples of n. Now, similarly, we have that z mod nz with addition is generated by 1 bar, the equivalence class of 1. And the reason why the generator of z gives us a generator of z mod nz is there are good reasons for that, which we will get into at a later point. So z mod nz is generated by 1, and that's basically because if we take the identity and we take 1 and we keep adding it to itself, we'll get 2 bar, 3 bar, etc. up to n minus 1 bar. And then if we add 1 to n minus 1 bar, we get back to 0 bar. And this is the set of all elements in z mod nz. Again, z mod nz has other generators. It has, 1 is typically not the only generator of z mod nz, but not every element will be a generator. In particular, 0 bar will never be a generator for any of these as long as n is at least 2. So these are a couple of good examples of cyclic groups. It's also helpful to keep in mind some non-examples of cyclic groups in case we run into the trap of thinking that every group can be expressed this way. So let's take a look at the group z mod 8z cross. Now remember, this is the multiplicative group consisting of all equivalence classes of numbers that are relatively prime to 8. So 1, 3, 5, and 7 are the positive numbers that are less than 8 and relatively prime to 8, that have no common divisors other than 1. And so I want to look at this group. And I claim that this group is not cyclic. And let's see why. What we can do is we can just look at the cyclic subgroups generated by each one of the elements. Now remember, we're working multiplicatively here, so the cyclic subgroup generated by 1 is just 1. That's just what we get by taking 1 and multiplying it by itself over and over and over and over and over again, and of course that just gives us 1 back. Let's look at the cyclic subgroup generated by 3. Well, it's certainly going to contain 3, and then it's going to take 3 times 3, which is the equivalence class of 9, but the equivalence class of 9 is the same as the equivalence class of 1, and so multiplying by 3 again will just get us back to 3, then get us back to 1, and so forth and so on. So in fact, the cyclic subgroup generated by 3 bar, it just has 2 elements, 3 bar and 1 bar. We could do the same thing here with the cyclic subgroup generated by 5. That's going to give us 5 bar. Then 5 bar times 5 bar would be 25 bar. But 25 bar is, again, 1 bar because 25 is congruent to 1 mod 8. And multiplying by 5 a bunch more times is not going to change any of that. And so the cyclic subgroup generated by 5 contains, or 5 bar contains 5 bar and 1 bar. In particular, it's not the whole group. And finally, if we look at the group 7 generated by 7 bar, we get 7 bar, then 49 bar. Well, 49 bar is also equal to 1 bar. And so we get a similar sort of construction occurring with each of the numbers that we look at. And so we see that no matter which element of the group we start with, if we construct the cyclic subgroup generated by that element, we don't get the whole group. And so since there is no element which generates the whole group, as a cyclic subgroup, this group is not cyclic. It turns out that cyclic subgroups are going to be very important in one of our main goals that we're going to be approaching this semester. One of our main goals this semester is going to be classifying and describing all finite abelian groups. And it turns out that the building blocks of this description, the way that we're going to describe them, are using cyclic groups. Cyclic groups behave in some ways like prime numbers. And just how every integer can be expressed as a product of prime numbers, every finite abelian group can be expressed as a combination of finite cyclic groups. We're going to get a lot more into that in the next few weeks. But this is our ultimate goal, and in order to really handle it, we need to understand cyclic groups pretty well. So that's what we're going to do right now. We're going to prove some things about cyclic groups, give some insight to their structure that will tell us how these most basic of groups interact with themselves, how they're structured, and so forth. So let's look at the first result, lemma 39, not a surprising result, but a very essential one. So let's let G be a group, any group now, H a subgroup of G, again, any subgroup at all, and let's let A be an element of H. In this case, we have that the cyclic subgroup generated by A is a subgroup of H. So this shows that if a subgroup contains an element, then it contains the cyclic subgroup generated by that element. This winds up being very important in results that we want to prove later. So let's go to the proof. So a lot of things that we have to prove for in order to prove that a subset is a subgroup, we don't have to worry about here. We already know that the cyclic subgroup generated by A is a group. So we only need to show that the cyclic subgroup generated by A is contained in H. As long as we show that it's contained in H, then we already know it's a group, so it has to be a subgroup of H. So let's do that. So let's let X be an element of the cyclic subgroup generated by A. And now here we're going to use the fact that we're going to use over and over and over again, this absolutely essential fact. Whenever you have some element that belongs to a cyclic subgroup, that means it can be expressed as a power or multiple of that element, depending on whether you're writing things multiplicatively or additively. So let X be an element of the cyclic subgroup generated by A. This means that there exists some n in Z such that X is equal to A to the n. That's what it always means to belong to the cyclic subgroup generated by an element. And basically every single time you are working through a proof and you wind up with something in a cyclic subgroup, you want to express it in terms of the generator or a generator of that cyclic subgroup. So there exists some n such that X is equal to A to the n. Since H is closed under multiplication, if n is positive, then A to the n, which is just A times A times A times A, n times, that has to belong to H, since A belongs to H. So that's what happens if n is positive. Now what about if n is negative? Since H is closed under inverses, A inverse has to belong to H. So since H is also closed under multiplication, if n is less than 0, then A to the n is the same thing as A to A inverse to the negative n. Now, in this case, negative n is actually a positive number. So that's A inverse times A inverse, dot, 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 times A inverse, n times. And so that has to belong to H. Now, of course, we haven't looked at all values of n. We need to include 0. It's easy sometimes to miss the 0 case when you're working through problems like this, not only in algebra, but in all areas of mathematics. It's very, very important that you don't, because there are lots of theorems that are true for all numbers except 0, and you want to make sure that you've correctly handled that case. So finally, if n equals 0, then A to the 0 is the identity. And we know from previous things we've done on subgroups that since H is a subgroup of G, then it has to contain the identity. So we have that in any case, X, which is A to the n, has to belong to H. So that means that the cyclic subgroup generated by A is a subset of H. Hence, the cyclic subgroup generated by A is a subgroup of H. So one way that this lemma tells us we can think about the cyclic subgroup generated by A is that it's the smallest subgroup of G that contains A. One way of constructing this cyclic subgroup, which is less constructive and less useful to us, but sometimes of theoretical interest, is the following. I take my group G and I take the element A inside it. Now G will have lots and lots of subgroups typically that contain A. I'll just take that whole big collection of all the subgroups of G that contain A, and I'll intersect all of them. And it turns out that the intersection of any number of subgroups is itself a subgroup. So we intersect all of those, maybe infinitely many subgroups, and what we get is the smallest subgroup of G that contains A. Well, what this lemma shows is that that smallest subgroup is in fact the cyclic subgroup generated by A. Because the cyclic subgroup generated by A is, of course, a subgroup containing A, but it's also contained in any other subgroup of G that also contains A. So that's another way of thinking about the cyclic subgroup generated by an element, which is occasionally of interest. All right, so let's go to the next result, which is very, very helpful in understanding the structure of cyclic groups. One of the main advantages of working with cyclic groups, particularly finite cyclic groups, is that we can use lots of results about integers, lots of results on divisibility and on greatest common divisors and even prime factors to help us out in understanding things. So, for instance, we have the following. Let's take lemma 40. I'm sorry, not lemma. This is a theorem. Theorem 40. Let's let G be a group, and A an element of G with the order of A finite. I'll remind us what that means in a second. If A to the K is the identity for some K, then the order of A divides K. So before we get into the proof, recall that the order of A is the smallest positive integer n such that A to the n is the identity. Now, if A to the n is never the identity, then we say that the order of A is infinity. But in this case, we're only looking for elements with finite order. That is, ones where, as we take higher and higher powers of A, eventually we do, in fact, wind up back at the identity. All right, so let's see a proof of this. Now, a hint, whenever you're trying to show that one number divides another, a lot of times what you want to use is the division algorithm. So, let's, for the sake of notation, let's let n be the order of A, and suppose A to the K is equal to the identity. If we want to show that n divides k, like we do, then a very common way of doing that is to write down the division algorithm when we divide k by n. So by the division algorithm, there is a unique Q and R in Z, with R sitting between 0 and n, and K equaling Qn plus R. So R's the remainder when we divide K by n. So therefore, we have that the identity is A to the K, but A to the K is A to the Qn plus R. And now we can start splitting things up. We can write this as A to the Qn times A to the R. A to the Qn is the same as A to the n to the Q times AR. Now, A to the n, by definition, is the identity. By definition, n is the order of A, and the order of A is the smallest integer, such that when you raise A to that integer, you get the identity. So this is the identity to the Q times A to the R. Now, of course, you multiply the identity by anything, you just get that thing back, and it doesn't matter how many times you raise that to a power. The identity times A to the R, even times a Q times, is just going to be A to the R. All right, so we get that A to the R is equal to E. But remember that the division algorithm says what R has to be. R has to be between 0 and n. In particular, it has to be less than n. If R were positive, we would have a contradiction. Since R would then be less than the order of A. So the order of A is the smallest number that you could raise A to get the identity. We're raising A to R to get the identity. If R itself were positive, then that would be a contradiction. Fortunately, we have an out. The order only takes the smallest positive integer. So if r has some way to not be a positive integer, then that's what it has to be. And of course we do. R is allowed to be 0. And in fact, it must be. Therefore, r has to equal 0. And that means that k is equal to q times n, which proves what we want, because that's q times the order of a, and this shows that the order of a divides k. So what does this mean for us? We're going to have a few corollaries of this that we're going to use as we move forward through the theory of cyclic groups. But the first thing that I want to talk about is just intuitively, what does this mean? So, intuitively, this means that the only powers of A which are identity are multiples of the order of A. So for example, if the order of A is 4, then we have that A to the 4th is the identity, A to the 8th, A to the 12th, A to the 16th, etc., etc., A to the negative 4th, A to the negative 8th, A to the negative 12th, so forth and so on, but no other powers of A are identity. So the only powers of A are the ones that are multiples of 4. And I should probably throw A to the 0th in there because that's certainly the identity also. But this leads us to something else, though. If we continue with this example, then let's say I want to know what A to the 17th is. Well, A to the 17th I know is A to the 16th times A. But A to the 16th is the identity, and I know that because 16 is a multiple of the order of A. So A to the 17th is just A. What about A to the 18th? That's going to be A to the 16th times A squared. So we get E times A squared, which is A squared. A to the 19th is A to the 16th times A cubed, which is E times A cubed, which is A cubed. And of course, there are lots of other ways of writing this. A is also equal to A to the negative 24th times A, because A to the negative 24th is identity, which is A to the negative 23rd. So we have that A to the, for instance, A to the 17th, A to the 1st, and A to the negative 23rd are all equal to each other. They're all different ways of expressing the same element of the group. And this, again, is where we get the term cyclic group from. As we raise higher and higher powers of A, we just keep repeating the same elements over and over again. A squared, A cubed, A squared, A cubed, and so on and so forth. This is hopefully reminiscent of what happens when we look at the elements of Z mod NZ, where if I take Z mod 4Z, then the elements of that look like 1 bar, 2 bar, 3 bar, 0 bar, 1 bar, 2 bar, 3 bar, 0 bar, and so forth and so on. In fact, the relationship here is strong. Note that 17 and 1 are congruent modulo 4. Their difference is a multiple of 4. In fact, we can see that quite clearly in how we've broken things up. 17 and 1 have a difference of 16, which showed up right here. 1 and negative 23 have a difference of 24, which showed up right there. Similarly, 18 and 2 have a difference of 16, which is a multiple of 4, which is right there, and so forth and so on. This type of pattern is exactly what we see every time we're dealing with a finite cyclic group. And the next corollary makes that really precise. So, corollary 41 says let G be a group and A an element of G. If the order of A is finite, then A to the I equals A to the J if and only if I equals J. Sorry, I miswrote here. This first part is if the order of A is infinite, then A to the I equals I to the J. A to the I equals A to the J if and only if I equals J. And then if the order of A is some number n which is finite, then A to the I equals A to the J if and only if n divides I minus J. And furthermore, we can write down exactly what the cyclic subgroup generated by A is. It's the set containing the identity A squared, all the way up to A to the n minus 1. And in particular, this is another place where we see that the order of the cyclic subgroup generated by A is n. We have n elements in this set, which is also the order of A. So we've mentioned this a couple times, that the order of an element and the order of the cyclic subgroup generated by that element are the same. And this is the corollary we would cite if we needed to for that. Before we move on, I want to just remember that this condition, n divides I minus j, is the same condition as saying that I is congruent to j mod n. So what this corollary is really starting to get at is that the structure of a finite cyclic group is intimately connected with the structure of Z mod n Z, which is based on the equivalence classes modulo n. And again, we'll make that very precise at a later date. All right, so let's see this proof that tells us about when elements in a cyclic group are the same based on their descriptions as powers of the generator. So let's suppose the order of A is infinite, and suppose A to the I equals A to the J. Without loss of generality, we may assume that J is greater than I. We haven't made any sort of statements yet about J or I. We haven't distinguished them at all, and so we can just go ahead and assume that J is greater than or equal to I should say. So now if we multiply on both sides by A to the negative I, we get the identity is equal to A to the J minus I. Now remember that we're working under the assumption that the order of A is infinity, which means that you can't raise A to any positive number to get the identity. So since the order of A is infinite, j minus I, well, it can't be positive, otherwise that would contradict the order of A being infinite, so it has to be less than or equal to 0, which is the same thing as saying that j has to be less than or equal to I. But we already had that j is greater than or equal to I. So if j is greater than or equal to I and j is less than or equal to I, that means that we must have that j is equal to I. So that proves the first part. Well, technically it proves that if a to the I equals a to the j, then I equals j, but the other direction is obvious. If I equals j, then a to the I obviously equals a to the j, because they're the same thing. So now let's consider the other case, and this one's slightly different. So now let's suppose that the order of A equals n, which is less than infinity. Let's suppose a to the I equals a to the j, and again, we'll have that j is greater than or equal to I. I don't know if we're actually going to need that this time. So again, multiplying by a to the minus I again, we get that the identity is equal to a to the j minus I. Well, here's where we can use the previous theorem. So by Theorem 40, since a to the j minus I is the identity, that means that the order of A must divide j minus I. So by Theorem 40, n must divide j minus I. At this point I can look up and note that I had written n divides I minus j instead of j minus I, but in fact that doesn't make a difference, because I minus j is just -1 times j minus I, so if n divides j minus I, it has to divide I minus j. N divides j minus I, so n divides I minus j. So that gives one direction. That shows that if a to the I equals a to the j, then n has to divide I minus j. On the other hand, if n divides I minus j, then that means that I minus j is equal to n times q for some q. And so we get that a to the I is equal to a to the j plus nq, which is a to the j times a to the n to the q, but a to the n is identity. And so all this cancels out to just be a to the j, and that finishes off the proof. Nearly. The last statement that the cyclic subgroup generated by A is this set of elements comes from the fact that the previous result, which means that any a to the n, or I shouldn't use n, a to any power k is equal to a to the r, where r is the remainder when you divide k by n, the order of A. So let me actually write that down. So for any k in Z, we have that a to the k is equal to a to the r, where r is the remainder of k divided by n, and that means that r lies between 0 and n minus 1. So that means that the cyclic subgroup generated by A, which is the set of all a to the n's, or a to the k's, I should say, where k is an integer, is just the set of a to the r's that we get, where r is a remainder when you divide by n, and so that's just a to the 0, a to the first, a squared, up to a to the n minus 1. And since a to the 0 is the identity, that finishes off the proof. So that tells us when two elements in a cyclic subgroup are equal. We can tell when they're equal by asking whether the exponents that describe them as powers of a generator are congruent modulo that the order of that generator. So let's go on next and talk about how we can get other generators for a cyclic subgroup. So let's take an example. Let's look at Z mod, let me not do that one. Let me look at Z mod 8Z, which is the set 0, bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, and 7 bar. So we've already seen that Z mod 8Z is a cyclic subgroup generated by 1. However, it's also a cyclic subgroup generated by other things. It turns out that Z mod 8Z is also the cyclic subgroup generated by 3. And so we can ask, all right, well, which elements of the set generate this cyclic subgroup? We can also look at some subgroup like the cyclic subgroup generated by 2. And the cyclic subgroup generated by 2 in this group is going to be the identity, 2, 4, 6, and stop. Because 2 plus 6 gets us back to 0, and so that's just it. Well, let's look at the cyclic subgroup generated by 6. The cyclic subgroup generated by 6 contains 0, the identity, 6. Now 6 plus 6 is 12, which is 4, mod 8, and 6 plus 4 is 10, which is 2 bar, and then 6 bar plus 2 bar is 8 bar, which is 0. So notice that this means that 2 bar and 6 bar are the same. This means that H is generated by 2 bar and by, not 4 bar, but by 6 bar. In fact, it's not generated by 4 bar because the set generated by 4 bar is just the set generated by 0 bar and 4 bar. So one thing that we will often want to do is to sort of get a standard representative for a given subgroup. So it's not immediately obvious when you look at the two descriptions, the cyclic subgroup generated by 2 and the cyclic subgroup generated by 6, that they're necessarily going to be the same. And so identifying when two cyclic subgroups are the same is often helpful when studying these types of groups. So let's look at Theorem 42. This one is a little more technical. So if G is a group, A is in G, and the order of A is a finite number n, then if I look at the cyclic subgroup generated by a to the k, where k is some integer, that's going to be the same as the cyclic subgroup generated by a to the greatest common divisor of n and k. And the order of the cyclic subgroup generated by a to the k is going to be equal to n divided by the greatest common divisor of n and k. So this is a situation where we're looking at an element A of finite order, and so it generates a cyclic subgroup that's of finite order, but then we're looking at the cyclic subgroup generated by a power of A. And we want to know what happens there. And that's what this theorem tells us. So let's see how that goes. So let's, for the sake of working through this problem, let's let D be the greatest common divisor of n and k. So remember that when you've got the greatest common divisor, one of the things that means is that there exist integers s and t such that d is equal to ns plus kt. That's one of the properties of greatest common divisor, is that it can always be expressed as a combination of the two numbers that you started with. Now, since D divides K, this means that there exists an integer Q such that K equals DQ. So this means that a to the k is equal to a to the dq, which is the qth power of a to the d, and that belongs to the cyclic subgroup generated by a to the d. And now, by lemma 39, that means that the cyclic subgroup generated by a to the k has to be a subgroup of the cyclic subgroup generated by a to the d. So that gives us half of what we're looking for. We're trying to prove that these two cyclic subgroups are equal. What we've shown is that the subgroup generated by a to the k is a subgroup of the subgroup generated by a to the d. So let's try going the other way. In order to get it the other way, we want to show that a to the d belongs to the cyclic subgroup generated by a to the k. We're going to use that by the expression that we had up above. So now we have that a to the d is equal to a to the ns plus kt. Splitting this up, that's a to the ns times a to the kt. Now we'll write this as a to the n to the s times a to the k to the t. Now a to the n is the identity, because n is the order of a. So that's e to the s times a to the k to the t, which is a to the k to the t. But that means that a to the d is a power of a to the k. That means that a to the d is an element of the cyclic subgroup generated by a to the k. Therefore, again by lemma 39, this tells us that the cyclic subgroup generated by a to the d is a subgroup of the cyclic subgroup generated by a to the k. So now we've got both directions, and thus this tells us that the cyclic subgroup generated by a to the k is equal to the cyclic subgroup generated by a to the d. So that gives us the first part of the story. First part of the story says that we can use the greatest common divisor of the order and the number k in order to give ourselves a generator of our group, of our cyclic subgroup. So the next step is figuring out what the order is of the cyclic subgroup generated by k. So now, so by corollary 41, the order of the cyclic subgroup a to the k is just the order of a to the k. So, furthermore, if a to the k to the m is equal to the identity, which is the sort of thing that we would need out of the order of a to the k, then that means that a to the km is the identity. And so we know from Theorem 40 n divides km. So the smallest number km that is divisible by n is the least common multiple of n and k. So in order for this a to the km to be the identity, well, obviously it has to be a multiple of k, that's by the construction, and by Theorem 40, km also has to be a multiple of the order of a. And the smallest number that does both those things at the same time is the least common multiple of n and k. However, we also have that the least common multiple of so next is therefore the smallest m such that a to the k to the m is the identity is the least common multiple of n and k over k. Because km has to be the least common multiple of n and k, therefore m has to be the least common multiple of n and k over k. Furthermore, the least common multiple of two numbers, n and k, is the same as the product of those two numbers divided by their greatest common divisor, which is nk over d, because we're using d for the greatest common divisor here. So the smallest m, such that a to the k to the m is the identity, is nk over d divided by k, which is equal to n divided by d, which of course is n over the GCD of n and k. So that means that the order of a to the k is equal to n divided by the greatest common divisor of n and k, which is what we wanted to show. All right, so let's see how we use this in a quick example. So let's let A be in G, where G is a group, and let's suppose that the order of A is 48. Now, we want to look at the order, the cyclic subgroup generated by A to the 20th. By Theorem 42, the cyclic subgroup generated by A to the 20th is equal to the cyclic subgroup generated by the greatest common divisor of 48 and 20, because 48 is the order of A, which is A to the, let's see, it's going to be A to the 4th. So that means that the cyclic subgroup generated by A to the 20th is the same as the cyclic subgroup generated by A to the 4th. So we have that the cyclic subgroup generated by A to the 20th is the cyclic subgroup generated by A to the 4th, which gives us the identity A to the 4th, A to the 8th, A to the 12th, A to the 16th, A to the 20th, A to the 24th, A to the 28th, A to the 32nd, A to the 36th, A to the 40th, and A to the 44th. We can stop there because A to the 48th is the identity again. Furthermore, we can see that the order of A to the 20th, the order of the cyclic subgroup to A to the 20th, is equal to the order of A, which is n, divided by the greatest common divisor of 48 and 20, which was 4. So this is n, this is the greatest common divisor of n and k, which is 12. And if you count the elements that we just did up here, we can see that that's true, that we had exactly 12 elements in our cyclic subgroup here. Theorem 42 is very helpful in understanding the structure of cyclic groups. There are a couple of corollaries we're going to write down, and then we're going to get to a big theorem which tells us about this structure. So, Corollary 43 is actually a much weaker form of a stronger theorem that we're going to get to later, but Corollary 43 is very important to talk about now. If G is a finite cyclic group and A is an element of G, then the order of A divides the order of G. So this is just applying the previous result. The proof of this is really just Theorem 42, where the order of A is going to be the order of G divided by the greatest common divisor of the order of G with some number, where this number k here is a number such that A equals B to the k, where B is a generator of the group G. But in particular, this means that the order of A certainly divides the order of G, because it's actually equal to the order of G divided by some integer. Corollary 44 says that let A be a group element, and the order of A is a finite number n, and for any integers I and j, the following are equivalent. So if we know any one of these, we know all four of them. So first, the cyclic subgroup generated by a to the I is equal to the cyclic subgroup generated by a to the j. Part 2, the order of a to the I is equal to the order of a to the j. And part 3, the greatest common divisor of n and I is equal to the greatest common divisor of n and j. So in particular, we have that the cyclic subgroup generated by a to the I is the subgroup generated by a if and only if the two elements have the same order, which happens if and only if the greatest common divisor of n and I is equal to 1. If and only if n, the order of a, and I are relatively prime. Corollary 44 is really just checking a few details from Theorem 42 and seeing that all of these are equivalent to one another. It's a very good exercise to prove Corollary 44 given Theorem 42. Let's take an example. Let's look at, let's let G be the cyclic subgroup Z mod 20Z. So we know that G is a cyclic group generated by 1 bar. We also know that the order of 1 bar is equal to 20. And that's because the order of 1 bar is the same as the order of the group, and the group G has 20 elements in it. So a number n, let me not use n, so a number m bar in G is a generator for G if and only if the greatest common divisor of m bar and of m and 20 is equal to 1. And this comes from the fact that m bar is equal to m times 1 bar, where m is an integer. So that means that the generators of G are 1, 3, not 6, 7, not 8, 9, not 10, 11, not 12, but 13, not 14, not 15, not 16, we get 17, not 18, and 19. That is to say, G is the cyclic subgroup generated by 1, but it's also generated as a cyclic group by 3, by 7, by 9, etc. So notice in this case that G is a cyclic group. To show that it's a cyclic group, we just needed to demonstrate one generator for it. But in fact, this group has 8 generators, 8 distinct generators. All right, the last theorem for today is our first example of a structure theorem. It's a theorem that tells us, given a certain algebraic object, it tells us what the interior structure of it has to look like based on, and it tells us about its subgroups and possibly how those subgroups interact with one another. It can tell us how to describe the elements of that group. We're going to get a number of structure theorems throughout the course, and this is our first one. So Theorem 45, and we could call this the fundamental theorem of cyclic groups. And there are a few parts to it. First, every subgroup of a cyclic group is cyclic. That by itself is already a pretty important statement, because this sort of statement isn't always true. Subobjects don't always have the same properties of the objects they sit inside. But in the case of cyclic groups, that's true. Every subgroup of a cyclic group is cyclic. If the order of a given cyclic group is n, then the cyclic group generated by A has exactly one subgroup of order k for each k, for each positive integer k, dividing n, namely the cyclic subgroup A to the n divided by k. So this tells us what the subgroups of a cyclic group look like. It tells us that if I have a cyclic group, all of the subgroups are themselves cyclic. Furthermore, we know that this tells us that for every divisor of the order of the group, there is exactly one subgroup with that order. So let's get into this and see how this goes. So let's do the first statement first. Every subgroup of a cyclic group is cyclic. So let's let G be a cyclic subgroup generated by A, and let's let H be any subgroup of G. At this point, we don't have any control over H. We want to prove that it's cyclic, which means that we want to show that it has some generator, that there's some element of H which generates the whole thing. So we'll get the trivial case out of the way. If H is just the identity, then H equals the cyclic subgroup generated by the identity, so H is cyclic. Let's suppose that H is not equal to just E, so that this means that A to the T belongs to H for some non-zero T. Now, the reason I know this is because this means if H is not just the identity element, that means that it includes some element of G. That's not the identity. But every element of G can be written as a power of A. That's the whole point behind G being a cyclic subgroup, or cyclic group rather. It means that every element of G can be written as a power of A. So if H is not the identity, and then that means that A to the T belongs to H for some non-zero integer T. Furthermore, since H is closed under inverses, we may assume that T is positive. because if it wasn't, then we just take the inverse of a to the t, and we get a to the minus t, it belongs to h, and minus t would be positive in that case. So this means that h contains powers of a, contains some positive powers of a. Let's let n be the minimum positive integer such that a to the n belongs to h. Here we're using the well-orderedness of the positive integers that we talked about way at the beginning of the course. That if I've got a collection of positive integers, I know there's always a minimum value in it. And so I'm just taking n to be the minimum positive number that makes a to the n belong to h. And so we claim that h is the cyclic group generated by a to the n. So first of all, we know that the cyclic group generated by a to the n is a subgroup of h. That's lemma 39 again. So now we need to show that every element of h belongs to the cyclic subgroup generated by a to the n. So now let's let a to the t be some element of h. So this t here shouldn't, let's see, at this point I am reusing a symbol, which I ought not to do, so let me use a different symbol here. I'll use u. Let's let a to the u belong to h. We know that every element of h can be written in the form a to the u because every element of g can be written as a to the u for some u. So we let a to the u be in h, and once again we're going to use the division algorithm. There exist q and r integers such that u is equal to qn plus r, and r lies between 0 and n. So here's our situation. Let me go ahead and give us a new page. I'm going to copy some of the last lines here. All right. That didn't work quite how I wanted. Sorry about that. This will be good enough. So, therefore, we have that a to the u is equal to a to the qn plus r, which is a to the qn times a to the r. Therefore, if we multiply a to the minus qn on both sides, we get a to the r equals a to the minus qn times a to the u. So I'll write that as a to the n to the negative q times a to the u. Now, a to the n belongs to h. That was our hypothesis on what n was. N was the smallest positive integer such that a to the n belonged to h. A to the u also belongs to h. That was what we started with. A to the u is just some random element of h. But in particular, this means that this whole expression has to belong to H. And that's because H is closed under inverses and is closed under powers and is closed under multiplication. So H is closed under all of these operations, and so all of this whole expression here has to belong to H. So therefore we get that a to the r is contained in H. However, again we have that r is less than n, and n, remember, was the smallest integer such that a to the n belonged to H. So again, similar to what we had before, if r is greater than 0, we get a contradiction, since a to the r belongs to H and r is less than n. And n had to be the minimum integer that made that happen, the minimum positive integer that made that happen. So therefore, r is equal to 0. So this means that a to the u, which belonged to H, is actually equal to a to the qn, which is a to the n to the q, which belongs to the cyclic subgroup generated by a to the n. Hence, this means that we took an arbitrary element of H, we wrote it as a to the u, because every element of our group can be written that way, and we showed that that element had to belong to the cyclic subgroup generated by a to the n, so we have that H has to be a subgroup of the subgroup generated by a to the n. But we already had the other direction, and therefore we have that H equals the cyclic subgroup generated by a to the n. So this proves the first part of our theorem, that given a cyclic group, any subgroup of that cyclic group will itself be cyclic. First of all, furthermore, we can describe its generator pretty easily. Just take any generator of your original group and then take powers of it, or multiples, until you get to the first one that lies in the subgroup you're talking about, and that will be a generator of that subgroup. So let's go ahead and do the second part of the proof. Of the theorem, rather. So remember that what we're trying to prove is the following. I'm just rewriting the second part of the proof down so that we can make sure we have it at hand. It says that if the order of a cyclic group is n, finite, then the cyclic group A has exactly one subgroup of order k for each positive divisor k of n, namely the cyclic subgroup generated by a to the n over k. So let's prove this. So let's suppose that the order of the cyclic group generated by A is n. Now, if we have some subgroup of the cyclic group generated by A, then by the first part of the theorem, H has to be the cyclic subgroup generated by A to the I for some I in Z, because every subgroup of a cyclic group is cyclic. By Corollary 43, the order of H is equal to n divided by I. Sorry, I think I had that. Sorry, I had that written down slightly incorrectly. We have that by Theorem 42, the order of H is equal to n divided by the greatest common divisor of n and I. So this means that the order of H divides n. Beg your pardon, I had a slight so sorry. Furthermore, by Theorem 42, H is equal to the cyclic subgroup generated by A to the greatest common divisor of I and n. So in particular, this means that every subgroup of A is equal to A to some divisor of n. And so these are the only subgroups of A that exist. And the order of H is n divided by GCD of Ni. So letting K be n divided by the greatest common divisor of n and I, we get our result. So it's really it's just an application of the first paragraph where every subgroup of a cyclic group is a cyclic subgroup, and from Theorem 42, every cyclic subgroup can be written as A to one of these divisors of n. So let's see how we can talk about this. So, as an example, let's let G be a cyclic group, and let's suppose that the order of G is 120. So we know that G has exactly one subgroup of order, let's say 10, namely A to the 120 over 10, which is of course A to the 12th. And we can write out what these elements are. We get the identity, A to the 12th, A to the 24th, A to the 36th, so forth and so on, up to A to the 108th. And we can also ask, how many subgroups does G have of order 7? And it has none. G has no subgroups of order 7, since 7 does not divide 120. G only has subgroups of orders that divide the order of the group. It's going to turn out that this is a true statement in general for all sorts of groups. the order of a subgroup always divides the order of the group that it sits inside. Proving that in full generality is going to take a little bit longer to work on, but this is a very important first step in that process. We can even work a little bit further here and get another numerical description of what the generators of how many generators a cyclic subgroup has. Corollary 46 is the last result we're looking at here. So suppose that G is a cyclic group of order n, and let's suppose that D is a divisor of n. The number of elements of order D in G is phi of D. Now this is defined to be the number of integers that are between 1 and D that are relatively prime to D. This is known as the Euler Totient function sometimes. The proof is pretty straightforward. So notice that any element of order D will generate a subgroup of order D. And by Theorem 45, there is only one subgroup of G of order D. Let's call it H, and let's say it's generated by A. And now if B is an element of G, and let's say the order of B is equal to D, then that means that the cyclic subgroup generated by B is of order D, but that means that it has to be equal to H, because there's only one subgroup of order D. So that means that the cyclic subgroup generated by B is equal to the cyclic subgroup generated by A. And so in particular, this means that B is equal to A to the I for some I. Corollary 44, however, tells us that the order of B is equal to the order of A, where B is A to the I, if and only if the greatest common divisor of N and I, or D and I rather, is equal to 1. So what that means is that the only elements of order D are the elements A to the I, where the greatest common divisor of D and I is equal to 1. And so the number of elements of the group of order I are the number of elements that satisfy this condition, where we're only interested in I between 1 and D, because D is the order of A. So we can use this to say how many elements of a given order a cyclic group has. So for example, we might ask, given a cyclic group G of order 40, how many elements of order 8 are there? And the answer, first of all, we check to make sure that 8 actually does divide 40, and it does. So the answer will be the totient function of 8. And so this is the number of elements, number of relatively prime numbers to 8 in the set 1 to blah, 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 up to 8, which in this case is 4, because because the elements 1, 3, 5, and 7 are all relatively prime to 8. Now we can identify those also in the following way. So we've got our set G, and it's, let's say it has generator A, and it has 40 elements. So E, A squared, A cubed, blah, 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 up to a to the 39. Now, we want our subset H of order 8. So that's where we're going to get all of our elements of order 8. And the subset of order 8 is given by taking the element A to the 40 divided by 8. You take the order of the group and divide by the order of the subgroup that you want. So that's going to be the subgroup A to the 5th. So that gives us E, A to the 5th, A to the 10th, A to the 15th, A to the 20th, A to the 25th, A to the 30th, and A to the 35th. Okay, so there's our unique cyclic subgroup, or our unique subgroup, in fact, of order 8. And now we want to know which of these elements here actually have order 8. And here's where we use these numbers right here. So the elements of order 8 are A to the 5th, A to the, I should write this as A to the 5th to the 1st, A to the 5th to the 3rd, A to the 5th to the 5th, and A to the 5th to the 7th, where these exponents are coming precisely from the totient function. They're all the numbers from 1 to 8, which are relatively prime to 8. So we get A to the 5th, A to the 15th, A to the 25th, and A to the 35th. So here are all our elements of order 8 in our group. So the takeaway from this is that cyclic subgroups have a very regular structure that we can analyze using arithmetic and a little bit of number theory, number sense, and that makes them very approachable and very useful for proving theorems. All right, so the last thing I want to talk about, which applies in much more generality, but is very useful to describe it with cyclic subgroups, is the idea of a subgroup lattice, which is a collection, or a diagram, I should say, of subgroups such that if H and K are subgroups of a group G, and H is a subgroup of K, then K lies above H with a line connecting them. So this is fairly easy to describe in terms of when we're looking at cyclic groups. So let's consider the group G, which is the cyclic subgroup Z mod 18Z. Now, the group G has certain subgroups. It has a single subgroup corresponding to each divisor of 18. So, if we go up divisors of 18, we have 1, 2, 3, 6, 9, and 18. Those are all the divisors of 18. Now, the subgroups with these orders are the following. The subgroup generated by 0 is the subgroup of order 1. It has only one element in it. The subgroup of order 2 is the subgroup generated by 9. Subgroup of order 3 is generated by 6. And you'll notice in these cases, after the 1, we're getting these subgroups by taking the order of the group and dividing by 2. So 18 divided by 2 is 9, 18 divided by 3 is 6, 18 divided by 6 is 3, 18 divided by 9 is 2, and 18 divided by 18 is 1. So this group only has 6 subgroups. They're all cyclic subgroups, of course, and we can put them in a lattice. Now, the largest subgroup here is the subgroup generated by 1. That's, in fact, the whole group. Now, there are a couple of subgroups below this. We've got the subgroup generated by 2 and the subgroup generated by 3. And they have no relationship to one another. Neither one is contained in the other, but they're both contained in the cyclic subgroup generated by 1. So next we'll look at the cyclic subgroup generated by 6 and the cyclic subgroup generated by 9. Now, the cyclic subgroup generated by 9 is a subgroup of the group generated by 3. And that's because 9 bar is 3 bar times 3 bar. It's a multiple of it. So the group generated by 9 bar is contained in the group generated by 3 bar. The group generated by 6 bar is a subgroup of the group generated by 2 bar because 6 bar does belong to, is a multiple of 2 bar, but 6 bar is also a multiple of 3 bar. And so we have this relationship as well. And then finally, we have the trivial subgroup containing just the identity sitting at the bottom. So this subgroup lattice can describe some of the structure inside a group, and if various cyclic groups, various groups in general, will have different subgroup lattices, and studying those can be a very fruitful avenue of exploration and study into seeing what kinds of properties a group might have.